Okay, today I'm going to talk about derivatives of inverse functions out of section 2.6 in your book. This is a topic that tends to cause people some confusion, which I'll explain. So let's start off and let's say that we know that g is the inverse function of f. And let's say we're ultimately interested in the derivative of g based on the derivative of f, and I want to show you what this connection looks like. So in this one, realize if this is the case that by the definition of inverse functions, f of g of x is equal to x. And keep in mind that does go both ways, so g of f of x would equal to x. But I have it set up this way because this is going to show us what g prime is ultimately. So once again, keep in mind the logic here is that I'm plugging x into g, and then f undoes it, and I'm back to x. Okay, so let's say we take the derivative of this thing. So what we're going to do is we're going to use chain rule here. So the derivative of the whole thing will be f prime of g of x. Then we take the derivative of the guts there, that's g prime of x, and that's equal to 1. So if I solve this for g prime of x, I get 1 over f prime of g of x. Okay, so look at the connection here. Based off of f prime, what this is saying is the inverse functions, their derivatives are reciprocals. Now the thing that's confusing here is it's not input to input, it's input to output. So what that means is if I'll show you one to confirm that this works. So let's say I have a function here, f of x, and it takes 3 to 7. And let's say I know that f prime of 3 is equal to 5. Let's say that's our derivative. Okay, now what that means is my inverse function, which I'm calling g, it means that 7 goes to 3, right? It undoes it. So I don't know what g prime of 3 is. I have no idea, but I do know that g prime of 7 is going to be the reciprocal of that. And this is the part that throws people off. So the input in f is going to correlate to the output when we do the inverse function g, when it comes to those derivatives. Okay, let me just confirm this with kind of an easy function here. Let's go with, let's make this kind of basic here. Okay, so I put our rule over here. So let's say we have our inverse function f of x, which I'm just going to call x squared plus 1, and we're only talking about the positive values of x to make sure that this is 1 to 1, okay? And that means that g of x is going to equal the square root of x minus 1, right? So I'm going to go minus 1, and that's going to be the square root. Now I'm not doing the plus or minus, once again, because we are talking about functions here. So let's just confirm that this does indeed work. Let's take the point, let's take the point, let's do 2, right? And that will give us the point for 5, okay? So what I'm going to do is I'm going to take the derivative of f, that's equal to 2x. Now, by the way, I'm just confirming that this little rule works. The derivative of g, I'm going to use chain rule here. If it helps, call that 1/2. 1/2 x minus 1 to the negative 1/2 times the derivative of that is 1, so I don't actually have to write that out. And so this would be 1 over 2. That is not a 2. 1 over 2 square root of x minus 1. Okay, so now just to show you how this works, f prime 2 is equal to 4. Now, what that means is, without even looking over here, that g prime of not 2, but g prime of 5 is equal to 1/4. All right, so let's confirm that that is indeed what we get. So g prime of 5 is equal to 1 over 2, the square root of 5 minus 1. And we get, surprise, surprise, that is going to be 4, so square root of 4 is 2, we get 1/4, and we are seeing the connection. So once again, when we have inverse functions, they are reciprocals, but it's not input to input, it's input to output. And that's something that you're just going to have to work through before you sort of convince yourself of that, okay? So let's move on to another example. So we'll actually call this the first example. So we have f of x equals 3x to the third minus x squared minus 8. And the one thing I want to point out to you, because this one is, if we actually solve this, we know that f of 2 is equal to, let's see, 2, that's 8, 24 minus 4 is 20, so that is 12. Okay, so now what I'm going to be interested in is I'm going to be interested in the inverse function, the derivative of that, of 12. So this is what I'm interested in. Now I choose this one, and the reason why is because this one is not an obvious one of what that what that inverse function is. So, you know, if you were thinking, oh, I'm not going to worry about it, I'm just going to find the inverse and find the derivative, that's going to be problematic here. Okay, so we do have to work off of this. So f prime of x is equal to 9x squared minus 2x, and the 8 of course goes to 0. So f prime of 2 is equal to 36 minus 4 is 32. Now, what does that mean? That means, oh, sorry. What we don't want f prime, this is what it's supposed to be, and this is where I get, what I wanted was f inverse prime. Okay, and this is what I was saying, this notation looks quite crazy. So it's f inverse prime. That's why a lot of times I just like to call the inverse function g, because we stay away from that really weird looking notation. So, and we're able to do it now. So what that tells me is f inverse prime of 12 is equal to 1 over 32. And that's how we end up using this in cases like this where it's not easy to find the derivative, or excuse me, it's not easy to find the inverse, but we know this connection here, so we can take the derivative of this, input to output, and then we can just do the reciprocal without even knowing what the inverse function looks like algebraically. Okay, in the rest of this section, our focus turns to specific inverse functions, and that is our inverse trig functions. At some point, I'm going to show you how to connect this. You know, as I said before, we have that formula of the inverse, the derivative of the inverse function of the reciprocal of the input to output. I'm going to show how that connects to this at some point. That's also true of e to the x and ln of x, because those are inverse functions as well. You can use that, use this inverse stuff in that context. Okay, now as I've been talking about, this first semester you're going to be able to use your notes. So this is no different. So you want to get these into your notes. When it comes down time for next semester into the AP test, we do have to have these memorized. Now, I will tell you that it is very rare that we see really any of these four. These are the big ones. These are the ones that show up the most on the AP test. Now, you should be responsible for all of these. It's not maybe quite as bad as it looks. When we take the derivative of arc sine, we get 1 over square root of 1 minus x squared. When we take the derivative of arctangent, we get 1 over 1 plus x squared. Those come up quite frequently. The derivative of arcsecant is 1 over x square root of the quantity x squared minus 1. Now, those three, if you know those, you know the cofunctions. And we talked about the cofunctions when we did the regular trig functions. So there's a connection here in that the cofunctions, arcsine, arccosine, they're the same except the cofunction derivative for the inverse is negative. So the same, but it's negative. So if you memorize these three, you just have to remember that these are negative, and that works. But, you know, in the meantime, you can have these written in your notes and refer to them as you need them in this first semester. Okay? But we still want to be moving along the way to memorizing these. So, you know, along the way, take the opportunity to sort of memorize them. Okay, so we're just going to work with some of these, and that will be it. Okay, I'm going to do these three derivatives. You know, for the most part, you just have those formulas. All the rules we've learned so far are still in play. So product, quotient rule. I didn't actually put a quotient rule here, but it's really going to be the same. The logic's the same, chain rule, etc. Okay, so I'm going to walk you through a couple of these, and you know, you're just going to have to practice this. They do look a little weird. Okay, so A, we want the derivative of this. So f prime of x. I'm going to do a different color here, just so it contrasts it. So f prime of x equals, so I use that formula for arcsine, which is the 1 over the square root of 1 minus blob squared, so that'll be x squared squared. I'll just leave it like that. You could certainly call it x to the fourth. And don't forget, chain rule, we got to take the derivative of what's inside. So that'll be 2x. You're perfectly fine leaving it like this. I will tell you the book has formulas that give you, they'll always put this in the numerator and probably call this 1 minus x to the fourth. But you know, what we're working on here, as I said before, is just the mechanics. I don't care about simplifying these things at all. Okay, this one here, we are going to use product rule like we always have in the past. Actually, we have chain rule on this, so we're going to take the derivative of this. Derivative of e to the 2x will be e to the blob. Take the derivative of the blob, so that'll be 2. Okay, copy down the arc tangent of x. Then plus, copy down the e to the 2x, and take the derivative of arc tangent, which is the 1 over 1 plus x squared. If you want to put that in the numerator, that is fine. I really don't care. Okay, last one. We are going to plug 4x into our formula, and don't forget we're going to do chain rule. So arc cosine will be the negative of arc sine. So this will be the square root of 1 minus 4x, that whole thing squared. If you want to call it 16x squared, that's fine. And then we're going to multiply that by 4. Okay, so that's taking derivatives using these inverse trig things. You know, they look a little weird, but the logic is exactly the same as what we've done in the past. All right. Okay, this is going to be our last example for today. You'll notice I dropped the numbers. I forgot what example I was on, so you can number them if you want. And I realize I wear a black shirt today, so I don't know if I'm disappearing. I haven't looked at the video yet, but it's possible that all you're seeing is my arms and head. For that, I apologize. That might be disorienting. All right, so anyways, so our last example today, we're actually returning to what I was saying at the beginning of the period, or the beginning of the video. What we want to do is find f inverse prime of 0. So what we realize is this is f, and ultimately we're going to take the derivative of that. So let's start off with that. We'll take the derivative of f. So f of x is equal to x minus 4 to negative first plus 3. So if I take the derivative of that, I get negative x minus 4 to the negative second. And then, of course, that goes to 0. So we call this negative 1 over x minus 4, and that is squared. So that's our derivative. So I want to remind you that usually this doesn't confuse people because this part of it doesn't confuse people. The inverse will be the reciprocal of that. What does confuse people is we're not plugging 0 into this, right? 0 is the output of this. So I've got to figure out what I'm inputting in this by solving what gives us 0. So I want to know when f of x is equal to 1 over x minus 4 plus 3. I want to know what gives me 0 there. So it's actually the output of the f that I'm plugging in because the output and input switch. And like I said, it's one of those things you're just going to have to work through before you feel all that comfortable with it. All right, so let's solve this. Let's move that to the other side. So this will be, let's see, 1 over x minus 4 equals negative 3. I'm going to cross multiply and solve. If you don't mind, I'm just going to kind of skip a step here because I'm running out of space. So this will be negative 1/3 on this side, and over here will be x minus 4. Okay, so just look at what I did there. I divided both sides by negative 3 and then multiply by the quantity x minus 4. So my x that I'm going to be interested in, unfortunately it is going to be a fraction, is going to be negative 1/3 plus 4. Now, since I'm going to get a common denominator here, or I need to add these fractions, let's call plus 4 12 over 3, so we have that common denominator. So what we're talking about is x equals 11/3. So we're clear what's happening. If I look at a chart here, f of x, if 11/3 goes into that, 0 comes out of it. So I'm interested in with my f inverse, if I'm interested in 0, these switch places. So I'm going to take 11/3 and I'm plugging it into f prime. So f prime, let me go with a different marker. So f prime of 11/3 is equal to, so this is my derivative, negative 1 over 11/3 minus 4. And let's call that 12 thirds, right? That's 4 squared. And so what I get here is negative 1/3. So I get f prime of 11 thirds is equal to negative 1 over, and that is negative 1/3 squared. So this is going to equal, that's going to be positive, so this will be negative. And I'm going to end up getting 1 over 1/9. So 1 over 1/9 means that this can equal negative 9. Okay, I'm really filling up the space here. So now what I know then is I know that f inverse prime of 0 is equal to reciprocal of this, which is negative 1/9. Okay, so let me just go through that one more time, because I know it is kind of strange. I don't think the derivative part of this, there's anything difficult about it. So we take the derivative f prime. The thing that tends to cause people issues is the input into our inverse is actually the output of our original, because that's what inverse functions do. So the work here is I've got to find what x value gives me an output of 0. So I need to solve this. I get x equals 11 thirds. Then that is what I plug into my derivative here, and had to deal with some fractions. I get negative 9. So that means my inverse for 0, flipping, is negative 1/9. Okay, so now let's take a look at this one. Actually, this is going to be easy. We've done all the work here. Find the equation of the tangent line to the graph of the inverse at x equals 0. So we already took the derivative at 0. So what I have is y minus, and we have this point, right? So that'll be y minus 11 thirds equals negative 1/9 x minus 0. Now that I realize it, I could have just wrote that in slope-intercept form because this is the y-intercept, but it doesn't matter. That's a perfectly fine form. Okay, so that's it for derivatives of inverse functions. I wrongly stated at some point in class, and I think maybe in a previous video, that we were done with our derivatives. This is actually it for the derivatives. We're going to be practicing this and mixing this up, and then at some point we're going to have a test over our ability to take derivatives and write tangent lines and things like that. Okay, so that is 2.6.